So first off, guys, there is still a lot of information. I know where it is, then maybe another time. If you cannot turn the camera on, that's okay. So, okay, guys. There is still much about delta epsilon that I have not discussed, but I noticed, you know, the material gets a little harder. I do ask you to read the full lecture notes on the definition of limits, and we might discuss more about it during, let's say, office hours. I will ask a pretty difficult question for the extra credit. Good? All right. So today's lecture, hopefully it will be something very interesting, guys. So let's review continuity. And there is one question in continuity that it's pretty difficult. So do you remember, guys, let's say before I show anything, could you type in the text, what is the definition of continuity at one point, at the point A? What is the definition? And then perhaps tell me why you think this definition captures the idea. Good morning, Alexa.
Oh.
Kirill, Uzai. We defined values before. Perhaps, guys, you see, so I already see the generation of this concept. It has to be extremely clear. And if you cannot put it in extremely clear words, that means that it begins to disappear from your mind. So first of all, what is it that we are trying to capture? The idea we're trying to capture is this is one piece, a connected object, yes? You see, you just intuitively know it. It's one piece. I move it around, it's one piece. Now, those two objects, well, it's not one piece. What's the situation there? What's the situation if the object we are discussing is, well, it's a wire or a curve, right? So you see this is a graph generated by the function f of x. So y equals f of x, it's a graph. Now this is not one piece because there is a hole in this fabric. Yes? This is not one piece. Why is there a hole? Well, in this case, because the function is not defined at a properly. It's this is a hole here. This is even worse here in the second part. Y equals g of x. You see that that not only is there is this fabric torn apart, you can see that there is a space between the left part of the curve and the right part of the curve. Good. And here and in picture 4, it's the same situation. So continuity at the point A means that the fabric is not turned at this point, right? So this wire is one piece, at least if you look at this point, it's fused together. Now, how do you know that it will be one piece? The idea is this. You see this? So I consider continuity at the point A to mean that if I trace the curve on the left and if I trace the curve on the right, the points converge to the same location, right? So I run my fingers along the curve, or I run my pencil along the curve, and the points merge in one location. That's pretty simple, yes, guys? So yes, you are trying to describe very meticulously and precisely what do you mean that a wire is one piece. So at least in the one location, that there is no tearing in that one location A. The points, as I stroke the wire from the left and from the right, I converge to the same location, and at that location the function is defined, so there is no hole. Okay, so limit as x goes to a of f of x, that means if this limit exists, that is that's already very close to being continuous. It's like it's at least or at the worst it's this situation in number 1. Yes, because maybe I still have a hole. And then to make sure that the hole is filled in, I define continuity at the point A to mean that limit as x goes to A, that includes left and right limit, equals to f of A. Do you understand the idea? So if you understand the idea, the definition cannot be forgotten. You understand how you're trying to capture the meaning here. Now, right continuity means that the limit as x goes to A from the right, from to A plus, it's f of A. That means here is an example of a right continuous function. So number 2 is a right continuous function, because if I move my x from the right of A, the place I merge is f of A. You see? This also is right continuous. Actually, sorry, there is no filled in, so it's not right or left continuous. But when the limit exists, that's called removable discontinuity, because all you have to do is, you see, just like this cursor, you have to fuse one point. You have to define f at A to be equal to this point here. So make sure, guys, to ask me questions right away. Yes, physically, but that's continuity, Anis. That's continuity over the entire domain. So here is an interesting question, for example, right? Could there be a function that's continuous only at one point? Can there be a fabric that's only connected in one point? Can such a thing exist? Just out of curiosity, you can type the answer, which is either yes or no. And that's a difficult question, possibly, right? But type, what do you think? Can such a thing exist or not? And we will move on afterwards. So if a function is continuous over a range of points, then you imagine it's connected everywhere. So in this case, it looks like it's connected from this value of x to this value of x, because everywhere I measure, the curve is intact. You heard my question, yes, guys? My question was, can there be functions that are continuous only at one point? In other words, a fabric that's a whole piece only in one location. So who says no? 3 people said yes. Interesting. I hope it's interesting. Who knows? Maybe you view it correctly. Maybe you do not. Yeah, so the answer is it could, but it's pretty hard to imagine it. I can write formulas for it, which tell you that it could be a fabric that's only connected at, think about it, one point, because what is one point? One point is at one atom. One atom is not connected, right? It's somehow merged in one location, but nowhere else. And I can give you examples of that maybe sometime later. So you all understand what's right and left continuity, guys. That means that as I move from the right or from the left to a particular location at A, that location at A is fused. Okay, so we worked, I think. Did we work? I'm not sure. I definitely did it with the other class. Did we solve question A, B, C, and D? Maybe we have not. Let's we might have not, right? So let's look at it again. Is A f of x equal to x squared minus x minus 2 over x minus 2? Where is this function discontinuous? And of course, why?
At 2?
Yes, thank you. Alexa, I think you spoke. Thank you, at 2. Is there any other point where the function is discontinuous? So you see, if I plug in 2 into the function, then I divide by 0, correct? If I divide by 0, that's impossible. That means the function is not defined at 2. So I definitely have at least the situation, you understand? So if this is 2, I plug it in, there is a hole. It's not defined. Okay, so as soon as the function isn't defined, it's not continuous there. Good. So this is not continuous at 2. And if I look at this expression every other way, in every other value A, if I push limit as x goes to A, I use all the limit laws. Again, remember guys, we haven't accomplished our main goal. I proved delta epsilon to establish limit laws, right? I would not go about using delta epsilon argument on every function. I would classify a huge range of functions for which I would right away know whether limits exist or not. So notice, if x is not a, limit of the quotient is the quotient of the limits. And then I have products, additions, and whatnot. I apply limits laws, and I verify that the result is the same as if I just plug in a. Look at it. You see, by algebra, continuity at point A means that if I take the limit, I get the same result as if I just decided to plug the value into the function. Take limit as x goes to a, just plug in a. So the only time when it does not work is when x is equal to 2. Now notice that if I factor the numerator, it's x minus 2 times x plus 1. And I can cross out x minus 2 when I take limit as x goes to 2. Because if x goes to 2, it's not equal to 2, and therefore I'm not dividing by 0. So I cross it out, and I see that the limit is 3. When that situation happens, so this is a case which is called removable discontinuity. In other words, we're dealing with the mildest type of discontinuity, which is type 1. You see there is a hole here, but the curves left and right limit merge. So all you have to do is just patch one point in, and the function becomes entirely continuous. In other words, f of 2 should be defined to be 3. Good? So we are done with A. Go ahead, guys, and tell me for B. Is the function continuous everywhere, or can you find a point where there is a discontinuity?
Can you hear me? Hello?
Hello?
Can you hear me?
Damn it. All right, good. Let's continue. So 1 over x squared is continuous everywhere. Okay, so guys, tell me where, if at any point, is in problem B, do we have discontinuity? What value is, yes, okay, so. Okay. Yes, Drago, at 0 the value is 1. Now, again, guys, right, I do want your input. Okay, so do you understand what I'm trying to verify? Because I only see a function, I do not see its graph, so I am blind to the shape of the string. I'm trying to figure out, I'm just close your eyes and just do this, right? You're trying to feel the string and make sure that the string at all the points is one piece. You understand? By one piece, you mean that, let's say, you see, why is this not one piece? Because you see the two parts of the curve, the left part of the curve from A and the right part of the curve from A are not fused together. They have to be touching. So the left and right part have to be touching, which means the limit has to exist. And you see there is this gap between my fingers. I don't want that gap. So it's a very difficult thing to imagine this gap, because this gap has dimension 0. You understand? You cannot see it in some sense, right? But you have to have this fusion. That's why I draw this big hole, this big circle. It's actually a circle that you cannot see. If they are touching, you cannot see it. Understand? But somehow there is a hole, like with my fingers. You see? So that the function is not defined where it is. The function is not defined where my fingers are touching. That's removable discontinuity. This one is a worse type of discontinuity. So first of all, what happens here? So at 0, the function is defined to be 1. Do you agree? F of 0 is 1. So it's defined everywhere. I can definitely plug into x a number that's not 0. I will use the top equation. And I can definitely plug 0 because that would be 1. Now the question is, so it's defined there, but the question is, obviously 0 is the only place of interest. Do you agree with me, guys? The only reason 0 is because everywhere else I use the limit laws. For any value a, the limit laws will tell me that's 1 over a squared. You follow me, guys? When I say limit laws, I hope it's not empty sound for you. So, by the way, type if you follow me, right? I need input. So say yes if you follow me so far. You understand what continuity is. That's extremely important. Thank you, guys. I really appreciate it. Great. So everybody understands. You see, that's how you think. You are describing in words. That's why mathematics is also a language. You describe what is it that you are trying to observe, and you describe it precisely. What is the limit as x goes to 0? It should be 1 if the function is continuous, but the limit as x goes to 0, it goes to infinity from left and right. So the limit here, that we're seeing this situation, right? It's defined to be 1 at, so it's type 3, although here we have at x equals 0, it's going to be defined to be something, you see? So it's this type of behavior, except that this line will be the y-axis. Good? So so part B, the function is not continuous at 0. And it's a pretty bad type of discontinuity because neither the left nor the right limit exist. Good? Now quickly do C. It's very similar to problem A, but now x is defined to, at 2 is defined to be equal to 1, the function. Not continuous at what point, guys? When you say not continuous, also tell me at what point. You understand? So we examine continuity point by point by point, right? So not continuous at a point A means that if I look to the left and to the right of, God damn it. Yes. So I hope, guys, the reason I said goddamn it is I just got a message that the internet connection is unstable. I'm hoping that I'm getting through. Yeah, so the wire, look at it. This wire is not attached properly from the left of 2 and from the right of 2. Why is that the case? We already examined that the limit should have been, so the limit is 3. So we know that the left and right hand limits, they exist, but the function is defined 1 at 2. It should be defined 3 at 2 to be one piece at 2. Make sense? So the next part, guys, is problem D, the greatest integer function. Where is that function not continuous? And let me help you with that. So in part D, let me explain to you what is the greatest integer function. So what you do is, it's called the floor function because you round down to the integer immediately to the left of the number. So for example, if I take 3.1, the function at 3.1 will round down to 3. The function at 5.9 will round down to 5. Or 5.999 will round down to 5. You just always, it's like you're between floors. If this is your integer slightly below the value, then you fall back to it. The function at minus 0.01, so you are below 0 and above minus 1. So you fall on minus 1. Make sense? So it's like you are between the 0 floor. It's like imagine gravity is taking you down. So you're falling on the floor immediately below your feet, unless you're standing on the floor. So if you're at an integer, so for example, what is the value of the function at 5? At exactly 5. Can you tell me? Type in the comment. The function here at 5 is what? Exactly, it is 5. So you understand how it works, but a function at minus 5.9, you fall to the floor below it. In other words, what's below minus 5.9? It's slightly above minus 6, so you fall onto minus 6. Make sense? So you understand what this function is doing, correct? It's called floor function because if you are between two floors, gravity will bring you to the lower floor. So the question is this: can you describe where this function, the set of all points where the function is discontinuous, and explain why? Go ahead, try to do that, guys. You can best do it. I would prefer if you do it blindly, but you can try drawing graphs of this function to have a sense of what it is. Okay, Lecky, that's nice. Ping also pretty good, yes. So it looks like a step function. But also train yourself to do that blindly. Most graphs, most curves are very complicated to visualize. Be more precise, Kirill, at which points do we lack continuity? And let's see who is here. Aryan, are you here? If so, type yes. Great. Kelly Prime Raj here? Wonderful. Rania Frederick, are you here? Rania Frederick? Good. Dana Phipps. Okay. So guys, sorry for distracting you. You remember the question. I'm asking you, where is the floor function not continuous?
I don't think it's continuous. I mean, non-continuous anywhere.
So you think it's continuous everywhere, Alexa?
Basically.
Okay, we will verify in a moment. You will see what we do.
Okay.
Okay, thank you, by the way, again for speaking. Arian, I think maybe you meant the other way around. But okay, so let's work through this example. So I did not draw graphs of it. I just do it, what you call it, by blind feeling. Okay. So do you agree that every number is between an integer, either equal to an integer or between two integers? Yes. That's all something that you actually prove, but we take it for granted. Good. So here is a picture. With me, guys? I haven't frozen. All right, so I drew it. I should have possibly drawn it vertically, right? So the floor function will make you fall down to the floor, okay? So let's see if we have continuity at some number that is not an integer. If a number is not an integer, abstractly, it is between the nth floor and the nth plus one floor. Do you agree? So I'm hovering. Imagine what I do is I take a person between two floors and I suspend that person in midair. Okay, so that person is in location A. Okay, now what's going to happen to this person? The value at A will be n. Do you agree? Because you fall back. Will be the integer below it immediately. Everybody agrees with me, guys? You see, I use abstract reasoning because I do not know where this value is. I just know that if a person is hovering between two integers, then I can label those integers as n and n plus 1. And then the value of the function at A will be this n. Yes? Now, if I take limit as x goes to A from the right, which means what? Which means that I eventually enter this space, and eventually I'm suspended also between integers n and n plus 1. Do you agree? If I want to visit this A, either from left or from the right, I will have to be at one moment, I have to jump to him, right? Imagine he's hovering in the air, I have to jump to him. So I'm somewhere here or I'm somewhere here, regardless of where I am, left or right, we all are our values. The value of the function at this point or at this point is just this n, which means the function is continuous. Do you agree? Because limit as x goes to A from either left or right is this value n, which is the value of the function at n. Do you agree so far, guys? I just proved that the function is continuous at non-integer values. Everybody understood my reasoning? If you understood, again, guys, please write yes, so that I know that.
Can you explain it one more time?
Yes, yes, Alexa?
One more time.
Yes,
yeah,
of
explain
course.
it one more time.
Yes,
Okay.
maybe you can explain, Alexa. It's much better when you explain than when I do it.
I kind of I kind of got lost when it became non-continuous.
Well, I didn't yet say not continuous. I just said, let me prove, you see, blindly, without knowing anything. And you see.
So that it's on the floor.
Yes, so we go to the floor. I mean, I drew it horizontally. Maybe I should have drawn it vertically. See, here is what I imagine. The floor function is bringing you down. It's like let gravity act on you, and then once it's done, I will tell you what's the value of the function, right? So that would be an integer always, yes? So let's show that the function is continuous everywhere where it's not an integer. So if you, so what does it mean? If you're saying, where are you? You're saying, I'm not an integer. So what you're really saying is that you are flying between floors. Imagine that we froze the frame and you are located between floor n and floor n plus 1. If you are not an integer, you are between two floors. And just label them arbitrary. The lower floor is n and the one immediately above you is n plus 1. That's just labeling. That labeling makes sense, Alexa?
Yeah.
Good. And so then what's your value? Your value would be the floor to which you fall, right? So you will fall to this floor. Now your friend wants to visit you. Your friend wants to get close to you. So your friend is either coming from above, from the n plus 1 floor, or from below. In other words, either jumping from the n plus 1 floor or heading up, right? So regardless of where your friend is located, if your friend is approaching your position in space, maybe you're at an escalator, I don't know, right? A friend is approaching. What would happen? The floor function will take your friend to n from either left or right, which means the limit. You see, limit means what? I'm pushing x towards a. So if x is very close to a but above a, or very close to a and below a, the values of as soon as it has to enter this interval, yes, as soon as it enters this interval, the value of the function will map it to n. The function will map it to n. You see what I'm saying? X is gonna go here. This x is gonna go here. So over this interval, the function is constant at n. Every point is mapped to n. Make sense? So what is continuity? Continuity is proving this limit. It's proving that limit as x goes to a is f of a. It is, because as x goes to a plus or a minus, the value of the function at that x is steadily n, and the value of a is steadily n. So they are agreeing. So I just established that the function is continuous at every non-integer. So if I'm not an integer, I'm between two integers, and the entire interval is mapped to n. Yes. Now let's see what happens if I'm at an integer. Suppose that I'm at an integer. In other words, suppose I'm here at the integer n, right? So if I push the point from the right, limit as I go to n plus 1, from the right will be also n. But if I try to climb to n, from below, it will bring me back to n minus 1, where I'm hovering my mouse, you see? So that means the function is always right continuous, because it's continuous everywhere, therefore everywhere for non-integers, therefore right continuous for non-integers. It is right continuous for integers, but not left continuous for integers. You see, because if I move from the left, I'm not getting this value, I'm getting the value below. But if I move from the right, I get this value. Does it make sense? I can draw the graph of it. This is a simple picture here, but no need for it. There is actually pretty interesting physics questions with where I used the greatest integer function. I can show you one afterwards, if anybody is curious. So I was very happy when I figured it out many years ago. Okay, so let's move on. So in general, many of the functions that you encounter are in many places continuous. So a function where you use multiplication, addition, division, and roots, radicals, that's called algebraic function. That's the most general type of function that we have dealt with. So polynomials, if you remember, only use addition and multiplication. Yes. Then you can create a bigger class of functions if you introduce division. Then you can create an even bigger class of functions if you introduce radicals. So algebraic functions are the broadest type of function that we have considered here. So you can show using the limit laws that in many places algebraic functions are continuous. In other words, they are continuous on all the values where they are defined. And here is this is just so 1 minus root of 1 minus x squared. It's actually the lower part of the circle lifted up, but let's not bother with this. So we want to show using limit laws that it's continuous everywhere on the interval from -1 to 1. In other words, I want to show that the graph, even if I don't see it, is one fabric. Okay, I always forget the English word for it. I mean a string perhaps, or what I prefer in German, it's called Faden, which means like, you see my clothing is made out of strings, right? So I'm not sure there is a better, string doesn't sound right to me. Anyhow, so if I take value thread, here you go. It's like I always forget the word thread, I lose my thread. But in German it's called Faden. Und ich werde meine Faden nie verlieren. Okay, so what you have is a value a between -1 and 1. And I push limit as x goes to a. And what do? I apply, you can see I apply all the limit laws for addition and subtraction. I have the limit law for the root, which I actually will, I will explain maybe later in the course why that works. So you can push limit into the root. Roots are continuous functions. And I evaluate blah, 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 and I get f of a. You don't need to go through all the steps. You just hopefully you understand that the limit laws make many functions, many limits for many functions very easy to calculate. So I get f of a. So I just established that continuity holds for any value between -1 and 1. Yes? Next, I want to establish that the function is right continuous at -1 and left continuous at 1. So what I do is I take limit as x goes to -1 plus, and similarly following the limit laws, I just get that it's f of -1. And if I take limit as x goes to 1 minus, I apply limit laws and I see that it's f of 1. The point, guys, again, is that I see that this function is continuous even without looking at the graph. I see that the graph has to be a whole thread, because I know that limit laws will make the graph intact at every point a. If you understood, please type yes so that I can continue. the point of this argument? Yes, good, good, great. I hope so. The main thing, guys, that I want you to grasp here is that although I could figure out what's the shape of the graph, I can actually make this thread visible when I'm giving a formula or a function for that thread. I do not know how it looks like. So I'm trying to use blind reasoning to know that this thread is a whole piece, even though I haven't drawn it. So here is a theorem which is an easy consequence of limit laws. If f and g are continuous functions at the point A, and then so is f plus g, f minus g, constant times f, the product of f and g, and the quotient as long as g of A is not 0. And the reason this works is because by the limit laws, we know that, first of all, that limit of f at x going to A is f of A, and the limit where x goes to A of gx is g of A. And then I use the limit laws for addition, multiplication, multiplication by constants, all that. Good? Division. So again, remember what polynomials are. They are going to play a big role in your understanding of mathematics. So if we have a polynomial, then the polynomial is continuous because I can evaluate the limit and I get P of A. Good? And the rational functions are quotients of polynomials. So it's a polynomial divided by polynomial. That's how you can reduce it to that form, right? Because if you have to use division, you can reduce it to the situation where you use division exactly once. Okay? You can think about it, see if you can reason it out. Not necessarily a formal proof, but can you reason that out? If you use multiplication, then it will be in polynomial form. Remember, constant plus a constant times x plus a constant times x squared and onwards. Okay, so I can group, if I use a multiplication and addition, I can group by the number of times I multiplied by x. Okay, constant means I multiplied by x 0 times, constant times x, that means I multiplied by x once, constant times x squared I multiplied by x twice, etc. So that's why you group it like this. But really, polynomials are just functions that only use the operation of addition and multiplication. Rational functions allow you to use one extra operation, which is division. Okay, that's why it's a bigger category. Every rational function is every polynomial, sorry, is a rational function because you don't have to use an operation. You are free to use more operations. That means you are free to create more functions. But irrational functions can be written as a polynomial over polynomial because when you have to use division, you can reduce to the case where you use division exactly once. Okay, that's why it can be of this form. And the rational functions are continuous for all values where denominator isn't 0. Okay, and here again, a remark is that I hope that you are already so savvy with limits that you don't think that when I take x going to A, I just plug in A. That happens frequently only because my functions that I'm dealing with are simple functions. They are rational functions or algebraic functions, in which case the result is very often the same as if you just put in the value A. Okay, but process-wise, conceptually, limits are entirely different. And for more complicated problems, limits give you entirely different results from just plugging the value A in. What you plug in is imitations of A-like values. Okay, that's what you do in delta epsilon. Okay, so we are at this theorem, which actually I can state, but because we haven't analyzed the structure of R, we will not be able to prove it. It's a name theorem, so it's very important. Intermediate value theorem. So this is what the theorem states. So suppose that we have a continuous function f, and it's continuous on the closed interval from A to B. And suppose that there is a value n, any value n between f of A and f of B, like I draw over here. So f of A is one point, f of B is another point, and there is a value n between them. The intermediate value theorem states that if f is continuous, then there must be at least one value c between A and B at which the function equals to n. So f of c equals to this value n. Now here is what you really are trying to, why that seems pretty obvious that there should be one such value. Imagine that the graph of this function, you haven't drawn it, so it's invisible to you. So it's an invisible thread. And you know one point that you were able to make visible, it's this point, and another point that you were able to make visible is this point. Now there is an invisible thread connecting this point to that point. If the function is continuous, it's a connected one whole thread. It doesn't have tears, right? If there's a tear, there might be a tear here, and then there is this tear here, and maybe there is no point here, right? But so somehow what this intermediate value theorem is saying is that this thread has to cross at least once this horizontal river, right? It has to cross this line at least once. Does this make sense, guys, intuitively? It's something that is, it's not trivial to prove it. And it's, if you're not dealing with real numbers, that's not true. Even though you might think of something that looks like a whole thread, but does it make sense? Do I need to explain more? And I'll give you examples in a moment. So it is something that, again, you can prove rigorously. It's a dangerous thing to just state, but for us, it will be hopefully intuitive enough that we see that this theorem should hold. Okay, you can make all sorts of very complicated. So it's actually it's a property of the real number system. If you don't deal with real numbers, that property can be shown to be false. But intuitively, it seems this. We are when I say my function is continuous, I'm saying that if I were to graph it, I will get a picture of a thread. But because I haven't graphed it, the thread is invisible. I have no idea where the thread goes, right? All I know is because I know the value at a of the function, I know one point is visible, and the value at b, that makes another point visible. So you have 1 point below this line, 1 point above this line, which means the thread crosses this this line n at least once. Maybe it crosses it many times. Maybe it goes like this, right? It might cross it 100 times or 1,000,000 times, or even maybe even, who knows, infinitely many times. But at least once there will be a crossing. Good. And that's what the intermediate value theorem. It's an existence theorem that tells you that there is a solution. What is that crossing? That means that if I plug c into my function, I will get n. Because f of c is n, right? F of a is this point, f of b is that point, f of c is this n. Okay, so that's what it says algebraically. So here is an example, guys. So we have the equation 4x cubed minus 6x squared plus 3x minus 2 equals 0. That's an equation, right? Can we find a value x that satisfies this equation, at least theoretically? Does this equation have solution? So we want to show that it has a root between 1 and 2. In other words, here's what I'm going to do. So you see this left part is a polynomial. It's p of x equal to 4x cubed minus 6x squared plus 3x minus 2, correct? It is a polynomial. And polynomials are continuous. So if I were to graph this polynomial, I will actually see a wire. Yes, I will see it. When I graph it, I see the wire. But let's say graphing can be tedious or complicated, and so I do not see the wire. It's invisible. So I'm going to make only a few points visible. So let's see what happens if I plug in 1. If I plug in 1, you can calculate. It's 4 minus 6 plus 3 minus 2. Apparently, you will get minus 1. Good? You plug in 4 minus 6 plus 3 minus 2, you will get apparently minus 1, right? And that's below 0. And so you see, I'm trying to show that there is a number that if I plug in, I will get exactly 0. You see, plug something in, and you get exactly 0. I plug in 1, and I'm guessing, right? I plugged in 1, and I missed. I got something below 0. And if I plug in 2, I get 12, so I get something above 0. You understand what just happened? Something like this. I got below my answer, except this should be the x-axis. I got below the answer, and with another value, I got above the answer, which means between my trial numbers, between a and b, there is a value that will give me exactly the answer by the intermediate value theorem. So let's just see. So write understood, sorry, right? So write yes if you understood. And as soon as you think something is missing, guys, you see, you just imagine it, right? You understand the idea here, because I imagine that we have a connected string, and because I haven't graphed it, it means it's invisible to me, but I know it's connected because the function is continuous. So that's why we had continuity, right? Continuity is an important assumption. The string is connected, so I have to connect one point to another point, and you see, if I have if I see this one point here and one point here, any value n between them, right, there must be a crossing with this horizontal line. The thread has to cross. Yes, good. So here is another example, guys. So all I know, I do not know if there is, you can analyze it further. I haven't solved the problem. I just figured out that there is some value between 1 and 2 that solves this equation. Maybe there's more than one value, but at least one exists by the intermediate value theorem. Good. Here is another situation. So we want to show that the equation cube root of x equal to 1 minus x has a solution or has a root. Okay, so we see this cube root of x. In other words, what is this equation saying in words? That there is a number that if you take its cube root, it's the same as if you just took 1 minus the number. You understand? That's what happens here. It asks you to find all numbers that if you take their cube root, you get 1 minus that number. Obviously, it's not all the numbers, right? So for example, let's try 8. The cube root of 8 is 2. Does 2 equal to 1 minus 2? No, it does not, right? So if I put here, 1 minus 8, right? So if I put here 8, cube root of 8 is 2. If I put 8 here, it's 1 minus 8, it's minus 7. 2 is not equal to minus 7. So 8 does not work here. Right? So is there a number that does work? So here is how we can try to do it. So first of all, this is our equation. Equation means it's not true for all numbers, so it's not an identity formula, right? So then what I can do is it's always nice to work with zeros, right? With real numbers, you can translate every equation into another equation that compares to 0. And it's nice to compare to 0 because then, you can easily tell if a number is, you don't have to worry about the magnitude of the number. You just have to tell whether or not the number is positive or negative. You understand? So every equation can be translated to an equation where something equals to 0. Just move whatever is on the right, move it to the left, and you have 0. Right? Subtract. In other words, whatever is on the right, subtract from both sides of the equation, you get 0 on the right. You see? So guys, again, so I'm not missing any of you. You understand what I've said, correct? You understand why I decided to move to make the equation equal to 0? Let's see. Can anybody type me in the comments or speak? Why did I decide to make equation relate to 0? So it's easier. Why is it easier? You see, I had this equation and I decided that I don't like this equation. I prefer to make the left part equal 0. Why is that the case? So
you have everything on the same side?
Yes, but why is that beneficial? This is not a polynomial, but why is this beneficial?
Keeps from getting confused?
I'm not sure, does it? Well, to plug in values to check if it's continuous or not, you don't plug values to check continuity. What you do so look at it, right? So imagine I asked you to carry a complicated calculation. Look at it. Look at the previous problem, right? So I calculated that at 2 it's 12, but really I can do much less algebra if all I need to know if the number is negative or positive. Do you agree? Look at it, right? I'm not sure how much experience you ever had with this, but it's much easier to say whether a number is negative or positive than actually to figure out its exact value. It seems obvious, right? I mean, you don't need to retrieve all the information about the number, only verify whether positive or negative. So I actually calculated 12 here, but I could have plugged in 2 and just ballparked it to see whether it's positive or negative. You see, like I plug in 2 here, I see, I see, okay, that's 2 cubed, etc. Right? So I haven't written it out. If you want to, after class, I can show you, right? So it's much easier to carry out, approximations rather than to carry the full calculation. Okay. So when I do that, 0, when I compare to 0, all I will need to do is to figure out whether I'm negative or positive. Okay. So what I have is this is my function. Now this function is continuous. Do you agree? F of x is continuous because, well, if I take limits, limits can be moved into roots by one of the. It's not quite a law. I mean, it's a consequence, but I will explain this consequence later. You can just take it to be true for now, that you can move the limit. So if I push x going to a-like number, the cube root of an a-like number is cube root of a-like. Okay, so I know this function is continuous as it uses algebraic operations. You can ask yourself, of course, could this be made into a polynomial? It's definitely not in polynomial form because I use cube roots, right? And cube root is not a multiplication operation, but maybe I can replace it by operations that only involve multiplication and addition. Think about it: when you press in your calculator cube root of 5, your calculator gives you values. What is it doing? That's an interesting question. You understand? Calculators, machines understand only addition and multiplication. In other words, calculators only understand polynomial operations. So it has to, so that's why it's very important to figure out how do you simulate more complicated operations using polynomial operations. Okay, but cube root, we will see later on in the course why cube root is not, strictly speaking, something that can be simulated by finitely many additions and multiplications. Notice I said finitely, okay? So whatever calculator is doing is an approximation. So it's not quite, it's not the right operation, it's just a very similar operation to the right one. Okay, so look what I have now. So I'm estimating whether a number is above 0 or below 0. I plug in 0 and I get -1. So -1 is below 0. I plug in 1 and I get above 0. Good. Which means that this string, which I have not visualized, this function corresponds to an intact thread. That thread is below the x-axis at 0 and above the x-axis at 1, which means it had to cross the x-axis. Okay, by the intermediate value theorem. Do you understand how I use the idea? Just intermediate value theorem is just trying to say this: if you have an invisible thread, one part of which you actually, just one point of which is below the x-axis, one point of which is above the x-axis, then it crossed the x-axis somewhere. So there must be a point C, at least one point. Maybe it crossed the x-axis many times. At least one value between 0 and 1 that solves this equation. So there is a number. I just haven't found what this number is. That when you take its cube root, it will give you the same thing as if you just wrote 1 minus the number. Good? Are you with me, guys? So to find out C, it's a different problem. The intermediate value theorem is an existential statement. It just means that it's possible to find such a number, but it does not tell you how to do so. You understand? It just tells you part of it. It's sometimes very useful to just know whether your efforts are meaningful, or sometimes it's just an intermediary step. You don't truly care about this number C. You're just using it as a stepping stone to show something or to find something that you do care about. Okay, so it's an existential statement. In other words, it says that this equation can be solved, that there is a number that satisfies it, but it does not tell you how to find it at all. And here is the next problem. Why do we choose 0 and 1? Just arbitrary values that are very simple. I could have chosen other numbers, right? I just see this equation and it's not so easy to calculate the cube root, right? I could have chosen 2, for example, 8, but 8 is a rather big number, right? At 8, it will be positive, right? At the cube root of 8 is 2, plus 2 minus 1 is positive. Notice I didn't calculate it, right? I said cube root of 8, which is 2, plus 2 minus 1. Oh, I didn't bother even finishing the calculation. I just right away realized it's positive, right? It's still not a hard calculation, but my point is that comparing to 0 is easier than than working, but then comparing to other numbers, for example, right? It's because if I compare to, let's say, 1, I need to know, is it bigger than 1 or less than 1? That's I need more information about the number rather than if I just comparing to 0, I just need to know positive or negative. So good. So I plugged in 1 just by instinct. I just trial and error. I just need to find one value below 0, one value above 0, right? And if I found the one hit below, one hit above, then in between there must be a solution. That's all the intermediate value theorem is stating, okay? And here is, that's a pretty interesting question. I might actually give you some time to think about it for the next class, right? So we have a Tibetan monk. He's leaving monastery at 7 a.m. and takes his usual path to the top of the mountain, arriving at 7 p.m. The following morning, he starts at 7 a.m. at the top of and takes the same path back, arriving at the monastery at 7 p.m. Here is the video of the mountain, so it's simpler for you, right? So day 1, you imagine you are working for National Geographic and you film how this monk is climbing this mountain from 7 a.m. to 7 p.m. He will be on the top. So the next morning, when you play the video at 7 a.m., he is on the top of the mountain and he descends to the bottom by the same path. What you have to prove, think about how you might do that. That in both videos, if you play the videos simultaneously, there is going to be a moment in the video where the monk is in the same location of the mountain on both videos, in exactly the same place. You understand? So somewhere when you move the time cursor, maybe to here, you will see that the monk is exactly, so the two pictures are identical. If you press pause, they are identical for the same time, you understand? I will be back, guys. Think about this problem a little bit and think how would you do that without even doing mathematics? How would you try to verify that if you had to deal with it? I'll be back. All right, guys, do you understand my question, first of all? So I will actually not answer this today, but do you understand the question, guys? You filmed the monk on his journey for 2 days, right? So the first day, the video runs from 7 a.m. to 7 p.m. And the second day, the video runs exactly the same amount of time. In the first video, the monk is at the base of the mountain and he walks along some path to the top of the mountain. That's where the video is over. So how can he walk? He might walk up, then he forgot something, he walks down. You don't know how he walks. He just walks in such a way that at 7 a.m. he is at the base of the mountain, at 7 p.m. he's at the top. Good? That's all I know. And in the second video, it's the same situation, but in reverse. He is on the top of the mountain at 7 a.m. and on the bottom of the mountain at 7 p.m. Obviously, he doesn't have to walk always down. He might walk down, then walk up, then walk down, then walk up. Doesn't matter, right? I don't know what he does. Only that he is in the same, well, he's at 7 p.m. at the bottom of the mountain. And then if you play the videos concurrently, so you see, if you were to press play somehow for both videos simultaneously, and then suddenly you realize there is a moment, that's what you have to show. There is a moment that if you press pause at that moment, let's say maybe the moment is here, where I'm holding my cursor, and here also, right? So the bars here are the same, where the pictures look identical. Where in other words, the monk is in the same place on the mountain on both days at the same time. Well, you cannot make any assumptions. You can, Anis, right? You can walk faster or slower, right? I don't know how he decided to walk on the first day. I don't know how he decided to work on the second day, but on the second day. But the statement is that on there is a moment of time in both days, same moment of time. In other words, this cursor will be in the same place. Obviously, it's not at 0. At 0, he is here in this video, and at 0, he is here on top of the video, right? On top of the mountain. So it's not 0, and it's not the final time. At the final time in here, he's like in this picture. So when time goes to 7 p.m., the monk will be here, right? So, but you're asked to prove that the monk will be in the same elevation at the same time. How would you do that? And maybe you can figure a way to make this maybe more obvious why that would be the case. Okay, so that will be. I will let you think about it. Maybe we'll talk about it on Thursday. Good. So that it's an interesting question. I want to say if you can figure it out, that that means you developed stronger abstract reasoning. So let me show you the next lecture, which is limit at infinity. Hopefully, extremely interesting lecture. Okay. And you know, I like paradoxes. I hope you're not tired of them. So infinity is, well, it has played a major part in my life, continues to play one. It's pretty much defining my existence. And let me give you a present. So I'm very generous. I hope you can see that through the video. If you want, I will offer you this amount of money. Okay. I will explain what it means, right? So I will give you right now $2 and 2 square dollars and 2 cube dollars and 2 to the fourth dollars and 2 to the $5 and ad infinitum. What I mean is you will have piles. You will have the equivalent of money in dollars, which is the infinitely many piles. One pile is $2. The next pile is $4. The next pile is $8. The next is 16, and so on and so forth. You understand? So imagine the piles. You're just staring at them. You have those piles. I'm asking you if you would like this gift. Hey, I want to see your reaction, guys. Right? Don't you like money? I will give it to you if you, well, especially if you show me in the video, like raise your hand, like, yes, give me this money. I want to see how many of you want it. Well, here you do. You signed in my class. So, yes, money for free. Come on. Come on. I need you on record. It's especially on video, so that I know that I don't forget to give it to the people that asked. So Steven, yes. Who else? I will show you as soon as you as soon as you decide to pick it from me. Promise. Strings are from the previous chapter, Ibad, right? And when strings are attached, you're saying you'll take it if it's not continuous. So you don't like continuous functions. I see. My God, I mean, you don't like my offer, or what's your problem? Most of yours are silent. You don't think I will give you this money? I will. So let's see who is there, who has signed up. So just to be sure, I will just from this, let's say, from this line. So money from below that, guys. Why in waiting room? Everyone in meeting. Is there anyone in waiting room? All right, so here again. Do you want money? If yes, then just say. In other words, this you understand, guys, what's my design, right? So I will give you the equivalent of money, the equivalent, right, that you will have if there were one pile containing $2 and another pile containing 4 and another pile containing 8 and another containing 16 and another containing 32 and onwards. You understand? Infinitely many piles, the equivalent. I don't have the infinitely many piles with me, but I will give you the equivalent of that money if you ask for it nicely. All right, so for example, some of you are not showing me your faces. I mean, I offer you so much, and so let's say, okay, of course I would Edwin, Ping, sure, Dana, yes. A bunch of you say yes, and it's on record, right? It's on record. It's a binding contract. Is it a trap? Well, the question is, okay, those that want it, what is it that you want exactly? What is it that you are going to get? You see, your problem is you use the word "it" very loosely and you forget what it means. All right, interesting. Irvin, yes, you definitely will have your money right now. Okay, so here is how you think of it, right? So are you getting something, right? You reach in, are you getting something, right? And you are saying, yes, you're getting something, right? So something is equal to this thing, to this pile, right? Let's see what that something is. So I use, look at it, the pattern here is pretty simple. What I put in parentheses is almost the same thing as S itself. Look at it, S starts with 2 to the power of 1. What I have in parentheses is 2 to the second power, to the third power, to the fourth power, and onwards. Good? What can I do to this? What can I do to this parenthesis to make it look exactly like S? Because it's infinite. That's important, right? If I just skip the 2 and I put everything else in parentheses, that's very similar to S. What do I do? Look at it. How can I make it 2 to the 1, 2 to the 2, etc.? All I need to do is just factor out a 2. Do you agree? Factor out a 2. And now this is 2 to the 1, this is 2 to the 2, this is 2 to the 3, and that's the same as S in this parenthesis. You see, I factored out 2. Do you agree? So this equation now of what I'm getting is simplified now to what? To S equal to 2 plus 2 times S. Do you agree? because what's in parentheses is s, right? Which means is that s equals to -2. So Irvin, you owe me $2. Everybody here that wanted it, you need to send me $2. Notice I was nice since it's just introduction. So did you, so Lee, use Lee, I think you also said you want something. I hope you did. Did I check? Let me see. So Yusuf Hassan, you wanted it for sure. So how many $2 bills am I getting? Irvin, for sure. You are going to send me $2 check. Stephen Lin. Well, you made the assumption you get infinite amount of money. Okay. Usually, you know, people are a bit more excited, but who knows? Maybe you're excited, you are just not showing it. You understand how I figured it out? I asked myself a very simple question. What is it that I'm getting? You see, I have this text message. It's on video. It's a binding contract. I can go to the court and say you owe me $2. There'll be more examples like this coming, you see. So what I did is this. I asked myself, am I getting something? Under the assumption that you're getting something, right? You say S, and that will be this pile, the equivalent of all those infinitely many piles, which then I just use my pattern recognition. I look at this entire sum and I realize that if I skip 2, everything in this red parenthesis looks very much the same. Yes, except that it's 2 to the power of 2. It should be 2 to the power of 1 to be S. So what I do is I factor out a 2. Do you see what I did, guys? It's very simple reasoning. Factor out a 2, and then I have this expression. And then what do I have in parentheses? I have the original S. It looks exactly like S. So I simplified. I avoided this scary, what is this entire thing? Does it mean? And I got S equal to 2 plus 2 to the S. Good. Infinity is very tricky. Okay, and whatever will follow will be a discussion of infinity, of course, right? Of how to deal with it, in this class. And I will not truly answer what infinity is, although Georg Cantor has a very, well, it has the theory that's used all the time. Well, so that's it for today's class. I stop the recording, and if you have questions, guys, stay with me.